Hey students, I've been wanting to make you a little solution video, and I think I'll do it this way. I'm not in my normal setting, so I'll just take my laptop and kind of turn it into a kind of a pad mode here and run through these questions. And I guess I'll just kind of write the answers here on a little sheet of paper, and then at the end we'll do a little summary here. So I'm hoping that would be helpful for a lot of you, and let me just take this as a moment to say, self-grade yourself. This is a good chance to then see what you did wrong and what you did right, and then get an idea of what your grade is before I finally get a chance this weekend to sit down and grade them, and then it'll also give you a chance to learn from your mistakes. All right, so let's go through this. Question number one. Question number one says a loop of wire is placed perpendicular to a magnetic field, and suddenly the magnetic field begins to increase. So hopefully you recognize this as Faraday's law of induction, and so there is a change in the magnetic field in this loop, so there will be some current, so we don't need to worry about this last one here. But we know that it opposes the change. So the little x's means that the field goes in, and since it says it begins to increase, so that means more goes in. And the idea of Lenz's law is it opposes the change. So there would be a secondary flux then coming out because it wants to keep it where it was. In other words, you might say that there's 4 little x's going in right now, and so if you turn it up, maybe that goes up to 6. And so to get rid of those, we need 2 coming up. And then I'm going to put my thumb up for the flux that's induced in the secondary and look at the current, which would be the direction of my fingers, and that is in a counterclockwise direction. So that would be B. So let me write down B here for number 1. I can't really do any. Oh, I can. Nice. All right. So there's B. All right. Now, again, it opposes the change. That means it wants to go back to where it was. So in other words, there's more flux going in. I'll call that the primary. Therefore, a current will be set up. Call that the secondary field set up that would oppose that change. And so that would be up. All right, so number 2. Number 2 says the 0.136 amp current through a 9.5 millihenry inductor is switched off in this much time. What is the induced EMF? All right, well, it's going to take a little bit of math to do this one. Let me just kind of bring my pad in here. But we learned that the voltage then is equal to, and technically a minus L, and then it is how does the current change with time. Now, not worrying about the minus sign, so let's just do absolute value. The inductance they have as 9.5 milli, okay. The current is going to be 2.77, and again, milli. So that would be the change in current, because we're switching it off, so it would go from this value down to 0. And then the time it takes, that was the time, 2.77 times 10 to the minus 3 milliseconds. The current is 0.138 amps. And so grabbing my calculator here, 9.5 times 10 to the minus 3, let me move this into the screen more, times 0.136 divided by 2.77 times 10 to the negative 3 gives me a voltage of 0.466. And so that would be the answer of B. Okay. Number 3. Number 3 says that we have a 640 kilohertz radio wave travels at a speed of Well, right there, since they're radio waves, since they're electromagnetic waves, their speed would be the speed of all electromagnetic waves, which is the speed of light. And so that means we've got to be either a C or a D here, okay? And has a wavelength of, okay, well, wavelength, or maybe I should put velocity equals wavelength times frequency. And when we rearrange it, the wavelength then is velocity divided by frequency. So the velocity is 3 times 10 to the 8th, and the frequency, and then just watch the kilohertz there, is 640 kilohertz. So 3 times 10 to the 8th divided by 640 kilohertz makes a wavelength of 469 meters, which I guess, bring this back into the screen, would be C. So number 3 should be C. Okay, nice. All right, another one here from our, I guess this is the second chapter in our sequence. 18, does that make it 19? But this is the laser beam, another electromagnetic wave. It says a bright red laser beam has a magnetic field with this much strength. Ooh. Okay, well, I don't like the way it divided the -5 Tesla. It could easily be overlooked, but maybe if you had a wider screen, maybe, I'm hoping it's just the way mine's set up, and I hope yours didn't divide right there, because you could miss that minus real easy. What is the strength of the electric field? All right, well, let me bring my yellow pad back here. But we learned that for all electromagnetic waves, the ratio of the electric field to the magnetic field is C, the speed of these electromagnetic waves. All right. So in other words, the electric field would be C times the magnetic field, and C being 3 times 10 to the 8th, and B being the strength of this field, which is 7.92 times 10 to the -5. So this would be 3 times 10 to the 8th, and I multiply that by 7.92 times 10 to the -5, and I'm looking at about 23,000. And to 3 significant figures, that would be 800, and that could be volts per meter or newtons per coulomb. Both are good options for the electric field. Let's see what our options are. Number 4. And so question 4 here, do we have that answer? Yeah, right there, 23.8. So I guess number 4 would be A, or 23,800 newtons per coulomb. Nice. All right. Number 5 here says, which color travels slower? So we're finally getting to the optics one. This must be the start of chapter 20. Which color travels slowly in glass or in water? Both have the same thing. And so if you remember our dispersion discussion, the answer for that would be the highest frequency. That would be the violet one. And then which color bends more when it goes from air into, so the change in speed, the amount of the change in speed is what bends it more. And that, of course, then would be the slowest one, because when it goes from air into glass, it changes its speed to slowest. So in other words, that would also be violet. So it sounds like our answer here for number 5 would be B, because the violet is the slowest. And then also, because it is slowest, it's the one that bends the most. The bending, remember, comes from the difference in speed. Number 6 says a movie projector shines a movie onto a large screen in a theater. The object is 3.15 centimeters. Watch our units here from the lens. And the screen is 12.5 meters. What is the focal length of this lens? All right, so switching to my notepad here, maybe getting myself a clean sheet here. This would be the 1 over the object distance plus 1 over the image distance equals 1 over the focal length. Now, the only real challenging of this question is making sure we get our sign convention done correctly, because we have positives and negatives for these, and we need to be careful with that. But the way this is described, you know, we've got this object here, and we want to project it onto a screen. We know that this could only be done then with a convex lens, because we got to get light out here. We have to have a real image. So this is positive images distances. So that means here we got to put a positive number there. Okay, so our object, and here's where I want to be careful with my units, it says it's 3.15 centimeters. And so I'm going to put that in as meters. And then my image distance, now that's what is projected up on the screen. So just kind of understanding the words behind this might actually make it a harder problem than the math itself. The math is, you know, okay, pretty straightforward. You put that number for object distance and you put that number for image distance. But knowing that this needs to be positive and that this needs to be in matching units, and knowing what each of the words mean, and so where they go, might be the hard part of this problem. But now we've got a little bit of math to do. So I can go, and there's different ways of doing this on a calculator. Let me do, I'll call it the more advanced way. Instead of just go 1 divided by, I like to do the 0.315 and hit the reciprocal key. And then add that to the 12.5 reciprocal key. And if I hit enter, I get those two added together. Now that doesn't quite equal F. To get F, I need the reciprocal of that. All right. And so that would be 0.0314. And hopefully that makes sense by fitting our intuition, because one of the things we said about making a real image on a screen and to make it bigger is the object needs to be a hair more than the focal length. If it is more than 2 focal lengths, then the image it makes is smaller than the object. And so I guess we don't really know if this one's going to be bigger or smaller, but it's kind of implied that way. And certainly if we sat down and did the magnification, which is minus image distance over object distance, we would see that's greater than 1. Anyway, so because it's so much bigger, we probably could have guessed that it's just a hair more bigger than the focal length. And sure enough, the object distance at 3.15 centimeters is just a hair more than 3.14 centimeters. And I've got it written in meters here. Let's see. Maybe I should write them in bold just so when I scan my answers, I'll know which one I'm looking for here. Let's see. And so coming back to number 6, they're all in meters. Okay. So I need the 0.0, there it is, 0.0314 meters. So question 6 should be A. All right. Going on to number 7, and again, you can see it's another lens one. And this says, what is the power of the eye, that is the lens, when viewing an object that is 1.75 meters away? Now, again, 7 is really almost identical to number 6 here, because we're going to do this 1 over the object distance plus 1 over the image distance equals 1 over the focal length. But the real key to this problem is not so much the mathematics, but it is recognizing that, okay, you got to use this equation plus what each of the ones mean. And so the object distance is probably the easy part of this problem, 1.75 meters away. But the thing to remember using the human eye is it is going to be a lot like the last problem where we have a lens and it gets projected onto a screen. In this case, the screen would be our retina. And again, we have to have the light really hitting there. We can't have the photochemical reaction take place unless the light actually then forms. And so my point is this would have to be a real image. And so this distance would have to be a positive, and it would have to be the distance from a human lens to the retina, which we learned is about in 2 centimeters for everybody. And so it's very, very close. I mean, even very, very large people with large eye sockets, it's, just 2.1. And so there's very little variation. And so that's why we said that, okay, this is the way to do this problem, is to always know that for the eye, the image distance is that 2 centimeters, which I'm going to write it in terms of meters. Now, again, like the last problem, that has to be positive. And then we have to then, in this case, find the power. Now, the power is defined as the reciprocal of the frequency. So we need to remember that. But it's also that much easier because we don't have to do that last step like we did in number 6 where we had to take the reciprocal here. So I'll just input these numbers, 1.75 reciprocal added to 0.02 reciprocal. And now I hit enter and stop right there. That is the power. And so the power would be 50, and rounding it to 3 significant figures, 50.6, and that's measured in diopters. And so for you life science people interested in optometry, you want to be an optometrist, these are the kind of calculations that hopefully will be interesting to you. Your job will be a little different than calculating these. It's, you'll be more of the human connection and the diagnosis and all that. But this would be your physics understanding of why we gave somebody a particular prescription, or whatnot. And I think that's coming up a little bit later. Anyways, and so looking at my options here for number 7, it looks like the 50.6 for number 7 would be B. Okay. All right, let's try number 8. And here's a nearsighted person. So a myopic student's far point is 37 centimeters. Okay, using contact lenses. So that was, I think, the easier one than the lenses. To correct the student's vision, what power of contact lens should be used to correct the student's distance vision? So remember, for somebody who's nearsighted, draw their eye. So this is the lens of their eye. They're nearsighted because they've got a little too much curvature for their eye. And the muscles that squeeze down trying to form an image on the retina here, when they fully relax, a normal eye should be able to focus at something really far away. But if you have eye troubles, which I do, I'm nearsighted, and then you have what we would call a far point. That is, when you relax your eyes here, you can get something in focus that's a certain distance away, which in this case is 37 centimeters. And sadly, you can't relax your eye anymore. That is, you can't lower the curvature anymore to focus on things further out. And that's why we say you're nearsighted. Everything from 37 centimeters in, your eye works fine with. So to correct the vision, what we like to do then is to put a correcting lens, which this would be a correcting for nearsighted, so it would be a little fatter on the ends than in the middle. And so as we go to correct, well, that's not the only way we can make a higher index on the edges. But as we go to correct the vision, here's the thinking. The thinking is take something that's real far away. Okay, so that'll be my object distance. And when the light hits the contact lens, and so there it's going to make an image, make it so that image appears to be at the student's far point. And that way, the eye can do the rest of the work. The eye can then focus on that far point, that 37 centimeters. So this is how we're going to figure out the power. Let's see, what was our question? The power, yeah. So like the last problem, we're not going to take the focal length, we're going to get the power of this. And the power would be the subscription or prescription that you would give the student and say, okay, this is the contact lens you will need to correct your vision. So in this case, we're looking at taking something really far away, so I'll say 1 over infinity, and making it appear 37 centimeters, and this is a catchy one and a tough one, negative distance. This is what I was kind of referring to on the other two here, where, you know, the equation isn't so hard, but the advantage of having this same equation for working for all the cases of all the lenses and all the mirrors is we got to pay close attention to the sign convention. Okay, and unlike these first two, where the image distance is positive, you know, here where we actually want to put the light on the screen so people can view it. Here we want the light to actually be on the retina, so the photochemical reaction of the rods and the cones can all take place. But in this one, we want the image to be, you know, outside of the eye. We want this to be in a place that, whoops, oh no, I bumped my finger here, my screen. Okay, how do I get, okay. Let me try that again. But, I was trying to tell you this tricky part of the negative. We want it to be on the virtual side where the light did not go. Anyways, and that's the negative. So I think if anything's tough on this problem, it might be right there with that negative. In fact, all nearsighted people then want to have the lens or the light be divergent. So all nearsighted people are going to have a prescription that has a negative number, whereas farsighted people will always have a positive. Anyways, this 1 over infinity we can just write as a 0. And so then this just becomes 1 divided by, I'll use the reciprocal key again, negative 0.37 reciprocal, and that is going to give us a negative